Okay, everyone, thanks for coming to Vault today, and thanks for coming to my talk. I'm Keith Busch, and I am a technologist at Western Digital. For those that know me from previous talks, that might be a little different than before. I've been at Intel. We're doing storage development for about 9 years, and joined Western Digital about 5-6 months ago, and onto the open source research group, and having a lot of fun there, doing all sorts of interesting open source projects. This one is I'd like to talk about today. It's called libnvme. This is the user space Linux NVM Express library. Unlike some of the previous talks, there's really nothing particularly innovative going on here. This is more just a very large task and organization. But hopefully it proves very useful. But we'll see. Just a legal disclaimer first. I might be talking about things that are going to happen in the future. I'm not 100% accurate on my future prediction capabilities, so some things maybe take with a grain of salt. So what's motivating us to do this? So NVMe is getting much bigger. It's getting a lot more features added to it. And so as the NVM Express protocol grows, so too does the driver supporting it. The complexity has grown tremendously. We used to have this really nice, lean protocol, and that just really is not the case anymore. And one of the great things that we have about having standards is that it should allow us to have common software interoperate across a broad spectrum of devices. That was the goal that we set out with NVM Express, and we have seen much convergence in some of the software, especially in the drivers. There really are not that many. You don't see many vendor-specific NVMe drivers anymore. You just have just the NVMe driver. And in Linux, we only have one. And this works across all fabrics. It works across all devices and different types. But in user space, this doesn't happen there. What we see in user space is every application that wants to do NVMe-specific things, they'll often re-implement a lot of the boilerplate code. Some do just cherry-pick just the features they want, and they just add on as needed. But we see a lot of the duplication everywhere, and some do it better than others. So for example, like NVMe CLI, that one implements a significant amount of the protocol, and then you'll see duplication in other command line tools, ls, SCSI, smartmon, they'll also duplicate a lot of the same stuff. So this duplication is something we'd like to avoid. In addition to the protocol that's changing, the kernel's APIs, they're very powerful. Some of them are a bit simple and abstract to use. We'd like to make that a little easier. So our goal with libnvme, we want to make all NVMe features on Linux very conveniently and reachable to all developers. All right, so where this fits in the software hierarchy. This is a user space library. Just want to make clear this is not about bypassing the kernel and doing things in user space. This is working with the driver. The NVMe driver that we have in Linux today, it essentially provides two different entry points to access your devices. One of them is through the block layer and the virtual file system. That's not something that we're trying to replace. So all your reads and writes, whether you're going through libaio or IOUring or just synchronous stuff, none of that's going to change. So you could make a libnvme IO engine, but that's not what we're trying to set out to do. So your fastpath stuff should all stay the same. This is purely about NVMe-specific protocol management. So this is your administrative tasks, like you want to check your device's health, you want to confirm their firmware is all up to date, things like that. That's where the libnvme realm comes in. And like I said, this is working with the drivers, not around them. So the delineation of responsibilities is quite clear. We're not going to implement things that are going to be destructive or harmful to the driver's operation. I mean, you could probably abuse the interfaces to do something weird, but we're not going to make it easy to do. So it's just going to try to implement the things that make sense to do from a user space. So this is just going to be sending those commands through the driver and decoding the payloads and things like that. OK, so where did we start a long time ago? It was quite a lean interface when we started. We had exactly one specification to consider. We had one transport, PCI Express. That's what we were considering when we developed NVM Express initially. And we had a very nice lean command set. We only have these 6 IO commands here on the right. And we have the 15 admin commands. I mentioned we don't want to interfere with the driver, so we don't even need to consider some of these admin commands. So these these 6 striked out ones, these would all be very destructive to the driver. So for example, like the abort command. You cannot, from the user space, control where your, for what submission queue a command goes on. You don't get to control what the command ID it gets tagged with. These are all responsibilities of the driver. So there's no way user space can successfully send an abort command to do exactly what they want. So, and not only couldn't it not target the specific command it wants, it can't even account for the abort command limit. So these are things you could use the library to send, but we're not going to make it easy to do. So we really don't have a whole lot to consider if we just have the early protocol to look at. Now, of the remaining admin commands that we have, there are various subtypes to these commands, and these change the operation of how the command works, the payloads that you need to set up or receive back. There really aren't that many, so we have only 2 identifications for your controllers and namespaces. We have these 3 log pages, and the 12 features that are just tunable configurations. There's really not a whole lot. If you wanted to make a library of all the admin commands, this is it. It's not very much at all. It's gotten a little more complicated since then. So here's where we are today with NVMe. We went from 1 specification to 3. You can make an argument there's even a 4th one, since there's a lot of NVMe specifics in some of the T11 documents for fabrics. We've extended our transports from just PCI Express. We now support RDMA, fiber channel TCP. And the NVM Express workgroup gave us this other transport, and Linux decided to use that as a loopback device. I believe that was thanks to Christoph for giving us that. That's a very convenient way to test our target code without actually needing any additional thing. It's a purely software-defined. A no-op transport. Very, very simple. We can test all of our fabrics, well, the non-transport specific part of the fabrics code without any additional hardware. Very convenient. The command set. So our I/O command set has doubled in size. We went from 6 commands, now we have 12. In my opinion, I would argue those reservation commands don't belong there. They are admin commands. These are not I/O commands. But they're there, so we can deal with that anyway. On our admin commands, got quite a few more, I think 27, but I've cross-striked out some of the others. Of the new ones, they keep alive as a fabrics command that would interfere with the driver, so no support there in the library. But still a lot of commands to consider from where we were before. And as before, we also have subtypes of commands. This is not all of them. This is just a bit of a snapshot of what we have. It's getting more and more complicated. We went from 2 identifications, so now we have 13. We have a lot, and a lot more log pages. Some of these log pages have sublog pages. A lot more features. We have dynamic namespace management to consider. The directives for setting up data placement hints, and the interesting fabrics opcode. This is a very bizarre opcode. It's the only opcode that defines subtypes that go in both directions for the data transfers. It's very weird, but fortunately, we don't need to consider this much from a user space, since a lot of this is low-level driver stuff for setting up your connections. So the only thing we really care about from user space is the property gets, which is essentially equivalent to PCI MMIO register reads. And that's just where we are today. I mean, there's a lot of new things coming in the future. As we heard from the previous talks, zone namespace is very exciting. That's something we would like to make easy to use from the library once those become ratified in public. But other people are talking about other things too. So computational namespaces are something people frequently talk about. They're abusing NVMe to do that today, so maybe they'll standardize it in the future. Who knows? Key value storage is always being talked about as well. And all this stuff is going to bring more logs, identifications, more features, and the command sets get bigger. Some people want to put spinning media on there. That's also going to increase some of the stuff that we need to consider in the specifications. Anyways, why am I talking about all this? Like, it's what I'm trying to express is like there's a lot of features that people end up duplicating out there. We'd like to kind of make this a little bit easier to use by having a single place, very consistent to use for all the applications that want to do NVMe nice things. So that's kind of what's motivating us to create such a library. And it's not just the NVMe protocol that got more complicated. The driver did too. In the original driver implementation, incredibly simple. We had exactly one device that we surfaced up to user space. And that device provided 2 entry points into the driver. We used typical generic block stack, which we're not interested in today. And then we had this special NVMe specific ioctal. And we only had 3 to consider at the time, just this namespace identification. It doesn't actually send any I.O., it just returns what the NSID of the device is. Then we have this admin command pass-through. And then we had this weird one, submit I.O. It was well-intended. Submit I.O. was developed back when we only had read and write I.O. commands. It was parameterized, very fixed to what those commands want. It was inappropriate for pretty much any other I.O. command. So it was a bit of a mistake, and we had to fix that up later. So today, this is a little closer to what we have. A lot more things that we're surfacing up to the user for you to consider. So starting from the left, we have these admin device handles. Well, we learned very quickly that sometimes you don't even have a namespace. So if you want to administer your device, if you needed a namespace to do it, you couldn't do it. So if your device was degraded, or maybe it ships from manufacturing without a namespace formatted on it, you got to have something. So then we created a new class of devices. These are the admin NVMe handles. And with that new class, we had to add sysfs attributes to link them up to. And the ioctals then, these also got a little more interesting too. I've crossed out submit I.O. It still exists. We're kind of stuck supporting it. Maybe we would really like to deprecate and get rid of it. It's just a bit of an eyesore. It's been replaced with the I.O. command. And something else that happened in the spec, all of our pass-through commands had just been 32-bit return types. Specification defined 64-bit return types, and that was wholly incompatible with the kernel's UAPI. So we basically had to double our pass-through command support to support the 64-bit types as well. Then linking back over to the sysfs side of things. This is what basically is going to define your whole hierarchy. You'd have to explore that if you want to understand the relationship between your controllers and your block devices. It's a good opportunity to mention something about what we did with multipathing. When we did multipathing, the namespace block devices no longer had a single controller parent, okay? So we had to change the naming scheme. The name no longer is tied to the lifetime of a controller, it's tied to the lifetime of a subsystem. So the name changed. People were very used to having a block device say it was NVMe 0 and 1. Naturally, they would think the controller that owned it was also named NVMe 0. That isn't true when you have multipathing. So the mistaken identity led to a lot of confusion. Some people performed operations on the wrong device, lose their data, unhappy customers. It was well-intended what we did, but it was just not quite right. If we had a library there, maybe we could have mitigated some of the problems because it can handle the relationships and establish them for you, but we didn't have anything like that at the time. And we have since changed the naming scheme, so it is more sane. Those mistakes won't happen, but that would have been nice to have avoided in the first place. And finally, we have this new device, this special controller handle, NVMe-fabrics. I guess you could think of this as just a container to handle the low-level initiator commands that you want to send to connect to new devices. And that one has an entirely different user API that's completely different than the rest that the driver presents. So the library wants to talk with all of these for you, and you only have to talk to the library. So all these different nuances, relationships of different devices, dealing with these special fabrics controllers, and it's all handled in the background, abstracted from the application so it can do what it really cares about. One other thing that the driver doesn't provide, but it is something to consider, a lot of the fabrics configuration stuff is persisted in a special file or set of files in the /etc NVMe directory. These are configuration files that are not particularly friendly to parse by a human, but the library can actually read them out, find out your persistent targets, and do all the discovery and connection for you. So just one more thing that you don't need to worry about. JSON, huh? No, the conf files aren't JSON. They're just key values, right? Right. Right, this is the initiator side. No, the J, yes. Yes. Okay. So all the features I've talked about, they're all implemented public on this GitHub repository. The link is there. Please feel free to browse it, break it, contribute, criticize, whatever. It's freely available. It's in the C language. It was made to be a C library, but you can include it from C++. There are examples embedded in the repository if that's your language of choice. So the code stats, yeah, so it's when you're trying to implement every single possible function and mode that the specification defines, this actually got much bigger than I thought. This library exports about 250 functions. It's quite large. But the code size is actually not that big to implement it. So it's roughly about 20,000 lines right now at the moment, but over half of that is documentation. I figured if you're going to have this many functions, if you want them to be easy to use, you're going to have to document exactly how they're used and cross-link everything with the with the different types that use it. And if you install the library, you're going to get 4 basic artifacts. You're going to get the AP header files that implement or define the API methods. You'll get a static and dynamic object, and all the documentation. So lots of man pages to define the functions and types, and HTML that's more friendly to read. So let's just dive into what that might look, to what that sort of looks like. At the lowest level of this API, we have the NVM types. This is where we're going to define everything the spec provides. So all the enumerated types, all of our structures, bit fields, masks, all that stuff, this is all defined here. It's way too much to really go into everything, so I'm just going to try to latch onto the NVMe telemetry log to just sort of drive this narrative. But this actually applies to pretty much all the types that NVMe defines. If you're not familiar with the telemetry log, it's a really cool feature. It's basically a specification-defined header, and then followed by a bunch of vendor-specific data. You could, let's see. I guess if NVMe was like an airplane, this would be like the flight controller black box data. So it's really useful to know if something goes wrong. So it's a pretty cool feature that not many devices implement yet. Anyways, so the documentation kind of looks like this. I've completely copied what kernel doc does. So if you're familiar with that, this should look very familiar too. As the specification changes, these types should be updated at the same day that the specification is ratified. So this should be kept in sync with the specification as we go. And the documentation has cross links for everything. So any particular fields, it should link back to that uses them. If there's a function that uses this, it'll link to that. So everything should be very easy to navigate. So now we have all these structures. We kind of need a nice, convenient way to access them. So we go to the next layer. This is where we're going to define commands. Our octal layer, at the very lowest level, it provides matching APIs that correspond to the kernel's UAPI. I specifically did not do the submit IO ioctal because we want to deprecate that. Everything is moved over to the IO command ioctals. This provides basically everything you would need if you wanted to send an NVMe command. You can send any arbitrary opcodes with arbitrary payloads. It is, however, a bit abstract. None of these parameters really define how they're going to use. It's really unconstrained. It's very inconvenient to use if you're a developer. You're basically going to have one eye on the spec constantly if you're coding to this API. So we need another layer that's going to make it a little easier, because we're not going to get our telemetry log very easily using this one. So we go one more layer. We have one function for every different type of command there are. So it's about 30 of them. These are parameterized and constrained to specifically what those commands want. It provides what you need and nothing you don't. This is quite a bit easier to use then. So this is our Git log page. We can more easily get our telemetry log. Like I said, we have enumerated values, so we don't need to kind of guess or look at the spec. We can just click on the enum type and see exactly what all the different logs are available. and then further documented to show what all the other parameters are. Now, get log, lots of different logs, so there's even log-specific fields. This is still too abstract for us to use to really conveniently get to our telemetry log. We can go one more layer deeper. So we got specifically for every single mode, we have another function, much more constrained to our to what we want. This applies to all the the log pages, all the identifications, all the features, directives, you name it. There's roughly 140 of them, or maybe more. There's a lot of functions for this. This is much more convenient for us to use. Now, but believe it or not, even still, this is still not good enough for us to get a telemetry log. Telemetry logs require a very complex sequence if you want to successfully get it. It's going to look something like this. So the telemetry log isn't even fixed. The data can still be changing, or it may not even exist at all until we get an event. We have to wait for the controller to tell us this event is there. That's going to come in via an asynchronous event. We can just listen for that through UDEV. Once we know that the event has happened, we know that the log is latched. So it's not going to change. After we know the log is latched, we can get the log size, allocate a nice big buffer for it, and then we can just read partially in a long loop sequence until we get to the end. Once we get to the end, we need to verify the sequence number. If we don't verify the sequence number and it's changed, then we know we've read a torn log and it's completely useless to send back to the vendor. So we need to verify it's correct. If it is different, something bad happened. Maybe the controller reset in the middle of the log. Maybe some other rogue application unlatched our data. But if it is good, we know our sequence is good, we've got a good clean log, then we can rearm the event. So we clear a bit called the retain asynchronous event in the controller. Now the controller is free to make new logs for us, and we just do it again. So this is a bit of a complex sequence. So the library provides a set of utilities for commands like this. I don't remember how many, maybe it was like a few dozen of them. But there's a lot of other commands that have complex sequences too that we would like to support to make it very easy to use. This is the API for that one. So this one, instead of actually taking a pointer to a log, it'll allocate it for you. So you don't know how big it is when you call this function. This one will allocate it all for you, and then you can tell it to clear the RAE at the end or not if you really want to. And that's it. There's really no other parameters. So this is very, very simple and convenient for us programmers to use. Next, going on to the fabric-specific stuff. So I mentioned this is a very unusual device. This is what handles initiating our fabrics connections. The user API for this, you have to write magical strings to this file. I don't believe this is documented anywhere outside the kernel code. So it's not particularly friendly to use. In order to make it a little easier to use, the library provides APIs that look very similar to the other commands. So if you want to connect to something, you fill out a structure very similar to what a command structure would look like. So now it's more consistent from a developer point of view. The intention here would be to update this one in sync if the driver changes. So we don't need to have a second place to document how this one works. Excuse me. And the last component I wanted to talk about, the NVMe tree. Now, I mentioned all the trouble that we had with people not understanding the relationship among all the devices. This is what would fix all that. NVMe tree will enumerate all the devices. It'll establish all the links between the block devices and character devices back to their sysfs nodes. It can group all the parent device hierarchies. So you got your subsystems, controllers, paths, and namespaces. And it will do that for you. If you wanted to visualize this in like an ASCII tree, that below is kind of like what you would get. So we have like one subsystem with several controllers and several paths, and then we have one simple PCIe device at the end. So it's a nice little visual so that way you can understand the relationship about how everything's constructed. Some systems can get quite large with a very mix of devices, so it would be very advantageous if you're writing some kind of administrative software, if you can filter what your software is even going to see. So like if you're your vendor Acme and you want to check all the controllers of the system, like are they up to date on firmware? You don't want to look at things that aren't your controller. So you can write filters that would selectively return only your controllers. Or maybe you don't want to see your PCI devices. You only want to see only the ones that are on another transport, not RDAM, that's RDMA, sorry. The intention with this component, keep it up to date with the sysfs hierarchy as it's changed. So yes, things do change quite frequently and fast. So what happens then if we change an API that is not compatible? So the intention, what we're going to do as far as maintenance goes, if we're going to have to change an API that's incompatible with the previous version, the symbols would get versioned. So that way, if you have an older application compiled against the old one, it should continue working if the library gets updated. So that should provide seamless upgrades if you do change the library. So backward compatibility is very important for this. There's still some work to remain. I would say about maybe 90% of the spec features are implemented. However, only about 20% of them are tested. There are a lot of very fringe features in the specification. I'm having a very hard time finding devices that implement them. So I can't say with 100% confidence everything is implemented correctly. So this is something I could use some help with to verify. There are also a few other features I haven't implemented. The ones that stand out are the persistent event logs and the management interface. I can't find any devices supporting these. And lastly, though, I do need to complete the integration with NVMe CLI. So NVMe CLI, I want to have completely separation for what the user interacts with and what the backend is. So libnvme provides the backend, and NVMe CLI will just do the user side. And I'm hoping if I can do this, NVMe CLI ships with a lot of distribution package repositories. So I think if I can slip libnvme in there, then maybe that could be like a Trojan horse to get distribution support. So I don't have to ask them directly, but we'll see. I'll have to actually talk with some folks to see how that should work. But we would like to see distribution support in there. Yes, Hannes. Yeah, good? Thank you. So Susie gives their blessing. And with that is the extent of what I wanted to show. It's just the beginning. There's a lot of work to do to finish this off, but we are well underway. I think we should be in a good spot to start integrating this in other places and avoid this duplication. Thanks. Any comments or questions? Or the question was, what is the license? That's a great question. I have to speak with some legal folks about this. I think I have cleaned it out from GPL contamination. I'm not sure if I have. I need to see if Christoph's code is in there or not. I want something a little more permissive. We're going for LGPL, maybe something MIT, but I have some legal work to do to confirm that. Yes, thank you for the question. Yes, please.
What relationship, if any, or interaction with IOU ring?
This does not interact with IOU ring. That is a different syscall. This is not intended to replace it. This is just primarily to use the iocto interfaces to do management-specific stuff. So yeah, good question. Yes, please. Reads and writes, yes. If you want to access your block data, this is not the library for you. This is purely as intended to provide the management capabilities. Oh, shoot. Yeah, so this is intended to do the management capabilities. This is like, so if you want to get logs, you want to see the device health, you want to update your firmware, those don't go through read and write path. That's a completely different path. This is to do. You could, but don't do it, okay? Yeah, like you could use this to do an IO engine and FIO with libnvme. You could. It just wouldn't be efficient. So separation of concerns here. This is the non-I.O. path stuff. So everything you want to do with your device that's not I.O. related, this is the library for you. Okay, I believe that is it. Okay, thanks everyone.